So this chapter is on Earth as a planet. We start out with just sort of a global perspective. It says, describe the components of the Earth's interior and explain how scientists determine them. And so you probably know from maybe middle school that the Earth has a core, a mantle, and a crust. The outer layer is the crust. It's a few miles thick under the oceans and maybe somewhere between 2 and 50 miles thick at the continents. The crust is about, half oxygen and a quarter silicon, and the rest of it's just a bunch of different types of metals. So, but it's mostly oxygen and silicon. It's the most common minerals on the compounds on the Earth's surface on the crust are quartz and feldspar. Quartz is just SiO2. It's like CO2, except instead of carbon, you have a silicon there. And it's the composition of quartz, but it's sand. Lots of dirt is just ground up quartz. Feldspar has a more complicated formula. You don't need to worry about it too much, but you see that XAlSi4O8. And so this would be, X is almost any metal like magnesium or sodium or calcium. And you can have any combination of aluminum and silicon that give you 4. So you could have AlSi3 or Al4 or Si4 or Al2 Si2 and then O8. So there's lots of oxygen and silicon around and aluminum, and so those just get mixed in and they bond in this particular way, and then you can stick a metal on the end of that because those are also pretty common. We'll talk about more maybe about why rocks and metals are so common in the inner solar system. We talked about it a little once before. And so the mantle, which is 1,500 to 2,000 miles thick, these are kind of roundish numbers depending on where you are on the Earth. It's underneath the crust. Its density is about, the density of the crust I didn't say, is about 3 grams per cubic centimeter. The density of water is about 1. So the rocks that you pick up on the ground are typically about 3 times the density of water. That's why they sink so easily in water. The mantle's a little denser than that. It varies between 3.5 and 5 grams per cubic centimeter. It's got similar composition. You can look, it's 45% oxygen, 22% silicon, 23% magnesium, and then there's other metals. So it's got about the same amount of oxygen, a little less silicon, and a little more magnesium, which is a little denser metal. And then there are other metals in there. And finally, you get to the core. The core's thickness is about 2,000 miles overall. So the Earth's radius is about 4,000 miles, or its diameter is about 8,000 miles. The outer core is about 1,300 miles thick, and it's liquid. And the inner core is about 700 miles thick, and it's solid. The core is mostly just iron and nickel. And so its composition is different. Again, you can see that these regions of the Earth have different composition. The Earth is chemically differentiated, like we said in the last section. Most planets are, and it's because they formed molten, and so the dense stuff sank to the bottom, and the least dense stuff is on the surface. And we'll talk about that more as we go. So let me see if I can pull up a picture of this. So there's that one, and right, so here's just a geology picture for a volcano. We'll talk about volcanoes as we go. This is a picture of the Earth taken by Apollo 17. We have a very cool looking planet we live on. So here's a picture of the Earth's crust and mantle and inner core and outer core, and that's sort of the standard picture you should see when you're a student in middle school or in astronomy class or geology class. Okay. So scroll down here to the next section. So how did we learn about this? Scientists learn about the interior of the Earth by using seismometers. These things measure vibrations. Seismometers use vibrations created by the Earth's seismic activity to look inside the Earth. That means, anytime there's sort of vibrations created by the Earth, like earthquakes or volcanoes, vibrations bounce around in the Earth, and these seismometers read them. It's similar to how a sonogram works on the human body, except sonograms, of course, are already producing their own vibrations. We don't produce the vibrations, we just listen. And so we kind of get a picture of the interior of the Earth by looking at these vibrations with our seismometers. Geologists do that. So describe the Earth's magnetic field and its origin. And so I'm going to give you a sort of a middle school view of this, but I think it's pretty effective. So the Earth's magnetic field is created in its interior. The solid inner core is spinning faster than the mantle and the crust, and the liquid outer core is in between. And so the friction between these moving parts separates charge. This separated charge produces a magnetic field as it spins with the Earth. And so I'm just going to give you a few examples of that. So let me just see if I can pull up this. So here's a balloon. And what I'm going to do is stick my head in here and rub the balloon on my head. And then I'm going to hold my arm up here. And you can see that the balloon is hanging from my arm. You may not be able to see it very easily, but I move my arm around here. Maybe I can put it on the side a little bit. I don't know if it'll stay on the side. You can sort of see that. Anyway, you can kind of see that the balloon is sticking to my arm. I'm moving my arm up and down, and the balloon is stuck to it, right? And so that's what happens when you get friction. Charge separates, and then since the Earth is spinning, now I can't get this balloon away from me. Since the Earth is spinning, that charge gets carried around in a circle. And so now I'm going to give you an example of what happens when charge gets carried around in a circle. This is just a bolt that's got thin wire wrapped around it, and I've got a paper clip here, and you can see that my bolt won't pick up that paper clip. Right? I can touch the paper clip to the bolt, nothing happens. But now I'm going to run a current through this bolt. What I'm doing is I'm wrapping. I have this copper wire wrapped around the bolt, and then I'm touching both ends of the copper wire to a battery, and you'll see that it'll now pick up this paper clip, right? If I release it, it'll drop it. And so the magnetic field is produced. Notice the wires aren't touching the paper clip; they're just wrapped around the bolt, and they carry current around the bolt in a tight circle. So basically, what I'm doing is I'm taking charge and making it spin around in a circle, and that produces a magnetic field. And so this is how the Earth's magnetic field gets produced. It's charge that gets separated inside the interior of the Earth, and then the Earth, in its spinning, creates a magnetic field by the moving charge. So as long as you have this friction going on inside your planet and charge getting separated and the planet spinning, you produce a magnetic field. Over time, though, as the planet cools off, that liquid interior becomes solid, and now you don't have the friction anymore, and gradually the magnetic field dies away. And so as planets cool off and lose their geologic activity, they lose their magnetic field. The Earth is still holding on to its magnetic field, but for example, the Moon and Mercury and Mars, that are much smaller, have already cooled off and have kind of lost their magnetic field. They don't have any friction going on inside, so they don't get any charge separation, and so they're not producing much of a magnetic field on their own. This is important. We'll talk about this a little later, in that the magnetic field of a planet protects the planet from ions that are being spewed out all the time by the sun. It's called the solar wind. They act like a shield or a barrier against the solar wind. And so as long as your planet has a good, strong magnetic field, which comes from having a molten interior and is spinning, you're protected. So let's talk a little bit about the Earth's crust, maybe. So there are three basic types of rock. Igneous rock, which is just sort of comes directly from volcanoes. Lava comes out of the earth in some region. It's got some composition. It cools off and makes a rock. That's called an igneous rock. The other type of rock you get is sedimentary rock. Sedimentary rock is formed in sedimentation. So, for example, as the wind and water erode a mountain, they carry granules of rock down into riverbeds or oceans. That rock gets built up in layers in sediment and eventually solidifies into a new rock. And so rock always starts out as igneous rock, and then it can be laid down, eroded and laid down, and become sedimentary rock. The third type of rock, there are only three general types. Well, there's a fourth one, but probably won't talk about it. Is metamorphic rock. And metamorphic just means changed form or different form. And the way that happens is if either igneous rock or sedimentary rock is super pressurized or superheated or something like that, it can change itself a little bit chemically and look a little different. And so we call that metamorphic rock. So those are the three basic types of rock we see in the Earth's in the crust. In the mantle, you really only get igneous and metamorphic because there's no sedimentation in the mantle. Okay, let's talk a little bit about plate tectonics. So let me go back to the other picture for a second. Let's see if I can page down here. There we go. So here's a picture of the Earth. Oh, here's the Earth's magnetic field. So this is, I didn't talk too much about the details of this, but maybe this is a, let me just take a second to sort of back up here and just talk a little bit about this. So here's the Earth's magnetic field. The magnetic field is lined mostly north to south. There are regions where it's fairly intense, these Van Allen belts, but you can sort of see, here's the solar wind. These are just highly ionized, very energetic particles that are coming off the sun because the sun is so hot and energetic. And these act like, you know, a rock in a stream where it just pushes the ions around or traps them and slows them down. Really, all you need to do is slow them down, and then they're just like hydrogen atoms or something like that, and they'll form water, and there won't be any problem. The only danger in them is if they would hit the Earth going really fast, and then they would be radioactive materials that would hurt us. But they're not. But the magnetic field protects us from that. Okay, so that was just a picture of some magma coming up. So if it's underground, it's called magma. If it's above the ground, it's called lava. And it's the same stuff. So this is a map of the tectonic plates on the Earth. The Earth has plates, and we find these plates through the seismic studies that we do of the Earth that sort of draw a picture of the Earth for us. And all of the seismic activity we see begins along these little plates. So when a vibration gets started from an earthquake or something like that, it happens on these plate boundaries. And so if the geologists just mark the epicenter of every earthquake they see, it just forms they all form the boundaries of these plates. And so all of these plates, it turns out, are moving in slightly different directions, and that causes weird things to happen. So for example, this red line here that's running up the middle of the Atlantic Ocean is called the Mid-Atlantic Ridge. And it turns out that these two plates, the African plate and the South American plate, are moving apart. And so new crust is being formed along this ridge in between these two. The South American plate is moving to the left in your picture, or to the west. And the African plate is moving to the right, and so there's a rift being formed here, and that's being filled in by magma and lava that's creating new oceanic crust underneath there. Notice this to the left, or west of South America, is this Nazca plate. It's moving to the right, and so that means it's being subducted underneath the South American plate. That is to say, it's being driven underneath the South American plate, and so we'll look at a picture of that. I think we will here in a second. Okay, let me just go back to the other figure for a second. So plate tectonics. Plate tectonics has to do with the fact that the Earth is composed of plates that move with respect to one another. When the plates move apart, it's called a rift zone. The mid-Atlantic ridge is one, where the European and American plates are moving apart. That's north of where we were talking about the African plate and the South American plate. And new crust is being formed along that center ridge. Subduction zones are places where one plate is sliding under another. This produces the largest volcanoes and mountain ranges. So the west coast of South America, for example, has large volcanoes and mountains. Faults are where plates are sliding past each other parallel to the boundary. I'll show you one of those in a second. We'll go back to that figure. Crust gets recycled into magma in the mantle after subduction. So the crust that passes under the South American plate is just going to be recycled and turned back into a crust in a mid-Atlantic ridge or someplace. So let me just go on down here for a minute. So explain rifts and subduction zones, and then I'll show you some pictures. Rifts are regions where the plates separating or moving apart. An example is the Mid-Atlantic ridge. A bulge underneath the crust can cause a rift. So can just continental drift, the plate tectonics moving apart. Subduction zones are regions where one plate is moving under another. So let me go back to these guys. So these are the top picture here is two plates that are moving apart, right? And so there's magma underneath. There can be all kinds of activity around it, but as these plates move apart, new material is being drawn up to fill in the gap, right? So that's a rift. Here's a subduction zone. Here's this plate on the right is moving to the left, and this plate on the left is moving to the right or staying stationary. And in this region, the plate on the right, usually an oceanic plate, is sliding underneath the continental plate. The oceanic plates tend to be a little lower. This friction can cause heat, which produces magma, which gives you volcanoes in those regions. And so that's how we get a lot of those things. You see this word, the lithosphere, here. So the lithosphere is what happens when the crust and the upper mantle sort of form an object together. The crust and the upper mantle are different chemically. They have different amounts of minerals in them and stuff like that. But as the mantle cools off at the top, it sort of acts as part of the crust, and you get what we call the lithosphere, which is, sphere of stone. Let me just go back up here for 1 second and give you this one. So you can see, for example, if you look over here at the west side of North America, this is a fault line. This is called the San Andreas Fault. A fault line is where two plates are moving past each other parallel, right? The Cocos plate, is that the one? No, what is it? This is the Pacific plate. Sorry, this big area is the Pacific plate, and the North American plate. The Pacific plate is moving to the southeast here, where it's next to the American plate, and the North American plate is moving to the northwest, and so they're sliding past each other. And that's called a fault line. The San Andreas Fault, if you have ever been to California, you can see it. And I think there's a picture of it down below here, if I'm not mistaken. Yeah, this is a picture of the San Andreas Fault. And so, all right, let me come up here to one other thing. If you've ever, I think probably everyone has looked at South America and noticed that it sort of fits into the Africa, right? The east coast of South America seems to fit into the west coast of Africa. And there are other areas where continents seem to fit together. Alfred Wegener proposed the theory of continental drift, the idea that these plates move past each other. He was roundly dismissed by the scientific community, but he was a very persistent man. And so, for example, he showed that fossils match. If you go back a certain amount of time, anywhere beyond that, the fossils match on the two sides of these plates. He showed that the sedimentation layers line up. If you've ever looked at like the Grand Canyon and you see the sedimentation layers in it, they depend on sort of what was going on in that region at that time. And he shows that once you go back a certain number of years, the sedimentation layers between these two plates line up. The magnetic fields in the local rocks. So, if, for example, if I have a volcano and the lava runs out onto the ground, it'll get magnetized a little bit in the Earth's magnetic field. And so it'll be north-south when it forms, but if the continent moves and twists, it may not be, that magnetization may not be north-south anymore. And he showed that they lined up between these continents. So he found all different ways that that he had to be right, and eventually people realized he was right. There was he found he matched up the continents just sort of all over the world and showed that at one time, most recently 250 million years ago, all the continents were sort of all together in one spot. It was a supercontinent called Pangaea. Um, that's pretty well accepted now. All right. So explain volcanoes. Volcanoes are due to tectonic activity. They can form um, when magma erupts through the crust due to heat produced by friction in the subduction zone. You can also just get a hot spot under under say an oceanic crust which is fairly thin. You can just have some magma under there that's really hot, and it will work its way up through the crust, and then you get a volcano there. But if the crust is moving, then over time you get a chain of volcanoes. And so, like the Hawaiian Islands are a chain of volcanoes that are forming over a hot spot in the mantle underneath the crust that's moving along over that hot spot.